Welcome to the lesson on defining manufacturing. Upon completion of this lesson, learners will be able to define manufacturing-related processes and key terms. Learners will also be able to differentiate between various types of manufacturing materials and classify manufacturing processes and operations. In today's world, manufacturing is a household term used within the context of our products and devices. But what exactly is manufacturing? What goes into the manufacturing process to create the products we use daily? It is the process of transforming raw materials into finished products using tools, machines, and labor. Manufacturing includes stages like production planning, quality control, and logistics, ensuring that the final goods meet specific standards and are delivered efficiently across diverse industries. The term manufacturing refers to the processes involved in the production of finished products using raw materials and machinery. In some industries, such as semiconductors and steel, the term fabrication is used instead of manufacturing. This transformation of raw materials into finished goods is now heavily dependent on machinery, but in its early stages, manufacturing was mainly a function of artisans. Manufacturing processes require a good understanding of the purpose of the process, the design of the components involved, and the specifications of the equipment used. Regardless of the process used, changing the properties of a material requires three factors: material, energy, and information. The general process model visualizes a material process using a flow system. In other words, it describes the production process in terms of material flow, energy flow, and information. There are three different types of material flow that a production process can have. These are described on the next slide. Material flow in manufacturing is the entire life cycle of resources within a production process. It begins with the extraction of raw materials and continues through various stages of transformation until the final product is created. This process involves the movement of materials throughout the production line, ensuring that resources are available when and where they are needed. The primary goals of effective material flow are to optimize production efficiency, minimize waste generation, and facilitate timely delivery of finished goods. Material flow is classified into three categories: converging flow, diverging flow, and through flow. We will discuss more about these categories in the upcoming slides. Converging flow in manufacturing is where multiple component streams merge at defined points during production. By integrating various components at specific stages, converging flow facilitates quality control, ensuring that each subsystem meets the required standards before being combined into the final product. This method is precious in complex manufacturing environments, such as BV production, where various components must come together seamlessly. In a typical EV manufacturing unit, the production flow involves several parallel processes that converge at strategic points. Battery cell production leads to battery pack assembly, while motor components and chassis parts are simultaneously processed into their respective assemblies. These three main streams converge at powertrain integration, where they're combined into a unified system. Meanwhile, electronics, wiring, and interior components are prepared separately. All these elements ultimately converge at final vehicle assembly, followed by quality testing. Diverging flow in manufacturing occurs when a single component or material splits into multiple streams during the production process. This approach allows for customizing different vehicle models or variants, enabling manufacturers to cater to diverse consumer preferences. Diverging flow facilitates the distribution of components to various assembly lines, ensuring that each production line receives the parts needed for its model. Through flow in manufacturing refers to the linear movement of materials or components through various production stages without merging or splitting. This method maintains a consistent pace of production, ensuring that each step occurs sequentially. In an EV manufacturing facility, the through-flow process may begin with the input stage, where raw materials like batteries, motors, and chassis components are stored in a dedicated area. These materials then flow into the main assembly line, which represents the processing stage where workers and automated systems assemble the various components into complete vehicles. Finally, the finished electric vehicles move to the output storage area, where they await distribution to dealerships or customers. Most of the objects we use every day were produced by specific manufacturing industries. However, some components of a product may come from a different type of manufacturing industry. Depending on the intended market, the products of manufacturing are classified as producer goods and consumer goods. Producer goods are products derived from a production process, but also used as inputs in the production of other goods for transformation or integration by other companies. Consumer goods are products created for a customer's direct consumption purchased directly by the general public. For example, producer goods and consumer goods serve distinct purposes in the economy. Producer goods include industrial equipment like factory machines, raw materials such as steel and lumber, commercial vehicles, and office buildings, all items used to produce other goods and services. In contrast, consumer goods are products used directly by end consumers, including everyday items like clothing, smartphones, groceries, and furniture. The main distinction lies in their use. Producer goods are used in the production process, while consumer goods are used for final consumption. Now that we understand material and product flow for manufacturing processes, how do we determine what a company can do? Process capability is formally defined as the extent to which the process meets the requirements defined by the organization's management and government entities. As such, a company's manufacturing capability is not just how much it can produce, but also considers the product quality resulting from its manufacturing processes. Manufacturing capability represents how much a company can produce that meets the company's standards. In common conversations, though, the term manufacturing capability describes the set of manufacturing operations, such as assembly or welding, offered by a company, or in other words, what the company can do. Next, we will discuss how companies choose the materials that they use for their production processes and the different types of commonly used materials. The selection of raw materials should be based on the material's characteristics and the requirements of the product to be created. The primary materials used in manufacturing include metals, ceramics, composites, and polymers. Ferrous materials, typically those with a lot of iron content, constitute a large portion of the materials used in manufacturing industries today. However, the use of man-made materials, such as plastics and composite materials, is consistently growing. We will discuss a few commonly used materials in the upcoming slides. Metals are solid materials which exist naturally and are good conductors of heat and electricity. Copper, aluminum, titanium, lead, bronze, and zinc are some of the commonly used metals in manufacturing. Such metals often form both the material being processed and the equipment used for the processing. Metals typically have high thermal and electrical conductivity along with some useful magnetic properties, and most of them become stronger when deformed. Some metals are highly ductile, allowing them to be stretched into relatively small diameter wires or rolled into thin sheets without breaking. Ceramics are inorganic, non-metallic, man-made materials created by shaping and firing a non-metallic mineral at high temperatures. Examples include glass, cement, and clay. These materials are very hard and react well to extreme heat. Some of them are even used as heat insulators, which protect other materials or humans from extreme temperatures. They are also excellent electrical insulators, which are objects or matter whose atomic structure does not allow carrying electric current. A composite material comprises several constituents that work together to produce unique features. As a result, composites can be designed to have unique properties, like high stiffness to weight and strength to weight ratios. They are appropriate for demanding applications due to their intriguing hardness and fatigue characteristics. However, one drawback of composites is that they can occasionally react negatively to chemicals, which could restrict their application in particular settings. The other drawbacks include high production and development costs, as these materials are not yet suitable for mass production. Polymers, from the Greek word poly, meaning multiple, and mers for a part, are chains of molecules. Polymers refer to a material made of the repeated combination of many smaller molecules. Each molecule consists of chain-like interconnected units called monomers. Polymers are widely used in composite materials and can be classified as plastics, including thermoplastics and thermosets or rubbers, also called elastomers. The main difference between thermoplastics and thermosets is the latter's intolerance for repeated heating cycles. However, both become liquid when heated and require lower temperatures for working than metals. This latter characteristic is also found in rubbers. Plastics are highly corrosion resistant and have low density compared to metals or ceramics. On the other hand, they are low in thermal and electrical conductivity. Disadvantages of polymers include their relatively low strength and temperature ratings. They cannot be used in extreme heat because they would soften or sometimes even deteriorate. Because of the variety of activities related to manufacturing, there are many valid methods of classification for manufacturing processes. However, the primary production processes recognized are casting, forming, machining, and joining, which can be grouped into two categories: processing operations, often called manufacturing processes, and assembly operations. The next few slides will discuss processing operations and assembly operations respectively. Processing operations are used to transform a material by changing its shape, properties, or general appearance. Thus, processing operations include machining processes, shaping and stamping processes, property-enhancing operations, and surface processing. Machining processes. Mechanical processes using various tools for altering metal, which may include cutting, grinding, turning, milling, drilling, or non-traditional machining, utilizing electrical or chemical processes. Shaping and stamping processes are mechanical processes where the original geometry of the metal is changed through forging, shaping, or stamping. Property-enhancing operations increase the value of the material being manufactured by enhancing the mechanical or physical properties without changing the shape of the material. Examples include heat treatment, alloying, and other surface treatments. Heat treatment modifies a material's microstructure through annealing and quenching, improving strength and ductility. Alloying involves adding specific elements to a base metal, boosting properties like corrosion resistance and hardness. Surface treatments, including carburizing and nitriding, strengthen the material's exterior, improve wear resistance, and protect against environmental factors. Surface processing involves modifying a material's surface properties while maintaining its bulk characteristics. The process begins with cleaning and preparation, where contaminants, oxides, or debris are removed to create a clean surface. This is followed by surface treatment through methods like shot peening, plasma treatment, chemical etching, or polishing to enhance the material's properties. Finally, surface coating may be applied using techniques such as painting, plating, physical vapor deposition, or chemical vapor deposition. The primary purpose of these processes is to improve specific surface properties like corrosion resistance, wear resistance, appearance, or surface roughness while keeping the core material unchanged. Assembly operations are used to combine several components into a new entity. They include mechanical fastening operations and permanent joining processes. In this slide, we will discuss more about mechanical fastening operations. Mechanical fastening operations is the joining of two or more materials without heating through the use of a fastener. Common fasteners include nails, nuts and bolts, screws and rivets, and mechanical interlocks. Mechanical fastening has many advantages, including the use of inexpensive tools utilizing commonly available skills and the production of a high-efficiency, high-strength joint with little or no damage to the mechanical properties of the material. The disadvantages of mechanical fastening include higher costs for fasteners, joint design limitations of the fasteners, and difficulty attaining pressure tightness. Mechanical fastening joins two or more items by using a fastener, but permanent joining processes, on the other hand, can be used to combine two materials without fasteners. Permanent joining processes are processes that fasten together two or more materials in a way that is not intended to be removed. Some types of permanent joining include welding, brazing, soldering, and adhesive bonding, which are described in detail in the next slides. Welding is the permanent joining of two or more materials into one mass by heating a metal to the point of melting, allowing the base materials, such as metals or thermoplastics, to flow together and form a bond. Welding is the most common type of process used in the assembly section of a plant, probably because of its adaptability. There are many different techniques of welding based on the conditions in which it is performed. In some instances, however, welding is not feasible due to the properties of the materials. Sometimes it is not economical. In these cases, other processes like brazing or adhesive bonding are then used. Brazing is a permanent joining process where base metals are bonded together using a filler metal, which is melted to fuse together the base metals. Soldering is a process where a filler metal is melted to form a bond between two or more base metals. Soldering differs from brazing in that it melts the filler metal at a lower temperature and differs from welding in that it does not melt the actual base metals. Soldering is typically used in more intricate or delicate assembly operations such as electronics, jewelry, and plumbing. Lastly, adhesive bonding is a permanent joining process where a substance, typically liquid or semi-liquid, is applied between materials, permanently adhering them to each other. Assembly tasks are important to manufacturing companies because the greatest efficiency gains, meaning more output with the same amount of input, generally come from assembly tasks. In summary, manufacturing is converting raw materials into finished products using tools, machines, labor, and the flow of materials. These finished products can be producer goods, which go on to another manufacturing process, or consumer goods directly purchased by final customers. Finished products are made of various materials, including metals, ceramics, composites, and polymers. Each type of material has its own advantages and disadvantages when used in certain manufacturing processes. Finally, this lesson discussed how all products are manufactured using processing operations, such as machining and shaping of materials, and assembly operations, such as joining and fastening of materials. Understanding these basic concepts is the first step to expanding one's knowledge in manufacturing. Thank you.